A step-index optical fiber is the simplest type of fiber. Imagine a straight, transparent straw. The core, the inner part of the straw, is made of glass or plastic with a constant refractive index N1. Right at the border of the core, the material suddenly changes to the cladding, which has a lower refractive index N2. This abrupt change is why it is called step. The index profile looks like a squared-off step when you draw it. N of R equals open curly brace. N1, 0 less than or equal to R less than or equal to A, N2, A less than R less than or equal to B, close curly brace. Where R is the radial distance from the fiber axis, A is the core radius, and B is the outer radius of the cladding. Light in the core hits the core cladding interface at an angle larger than the critical angle, so it is totally internally reflected and stays trapped inside, much like a marble rolling inside a smooth circular bowl that has a steep wall. The constant indices make analysis easy, but they also cause each ray to take a different path length, which leads to intermodal dispersion in multimode step-index fibers. Explanation: the numerical aperture NA tells us how much light a fiber can collect from the outside. It is defined as NA equals square root of N sub 1 squared minus N sub 2 squared. Think of NA as the width of the mouth of the fiber. A larger NA means the fiber can accept light coming in from a wider range of angles. The acceptance angle theta A is the maximum angle measured in air at which light can enter the fiber and still be guided. It follows from Snell's law. Sine of theta A equals NA. Or equivalently, theta equals arcsine of NA. Example: suppose a step-index fiber has N1 equals 1.48 and N2 equals 1.46. Then, NA equals square root of 1.48 squared minus 1.46 squared equals square root of 2.1904 minus 2.1316 equals square root of 0.588, approximately 0.242. Thus, theta equals arcsine of 0.242, approximately 14 degrees. This means any light that hits the fiber face within about plus minus 14 degrees from the normal will be trapped inside the core. The NA is also useful when coupling light from LEDs or lasers. The larger the NA, the easier the coupling. V number or normalized frequency combines the fiber geometry and the wavelength into a single dimensionless quantity. V equals 2 pi A divided by lambda times NA, where A is the core radius, lambda is the wavelength in free space, and NA is as defined above. The V number tells us how many guided modes the fiber can support. Single mode condition. For a step-index fiber to support only the fundamental mode LP0, 1, we need V less than 2.405, the first zero of the Bessel function J0. Sample calculation. Let a fiber have core radius A equals 4.5 micrometers, and A equals 0.12, and operate at lambda equals 1.55 micrometers, typical telecom wavelength. V equals 2 pi times 4.5 times 10 to the minus 6 meters divided by 1.55 times 10 to the minus 6 meters times 0.12. That equals 2 pi times 4.5 divided by 1.55 times 0.12. Approximately 28.27 divided by 1.55 times 0.12. Approximately 18.24 times 0.12. Approximately 2.19. Since 2.19 is less than 2.405, the fiber will operate in single-mode regime at 1.55 micrometers. If we change the wavelength to 850 nanometers, the V number would increase and the fiber could become multimode. The V number is a handy design tool. By adjusting O or NA, you can set the cutoff wavelength for single-mode operation. Explanation: in a step-index fiber, each guided mode has a propagation constant beta, which tells how fast the phase of the field travels along the fiber axis. For a mode M, beta sub M lies between K0N2 and K0N1, where K0 equals 2 pi over lambda is the free space wave number. The field distribution for the fundamental LP0, 1 mode can be written in cylindrical coordinates as E of R, phi, z equals a times J0 of U R over a divided by J0 of U times e to the j beta z, 0 less than or equal to R less than or equal to A. where J0 is the Bessel function of the first kind. U is a normalized transverse wave number satisfying U squared plus W squared equals V squared, and W describes the exponential decay in the cladding. E of R comma phi comma Z equals a times K0 of WR over a divided by K0 of W times E to the J beta Z, a less than R less than or equal to B. With K0 the modified Bessel function decaying. The mode field diameter, MFD, is often approximated for the LP0, 1 mode as MFD approximately equal to 2W0, W0 approximately equal to a divided by open parenthesis 0.65 plus 1.619 over V to the 3 halves plus 2.879 over V to the 6 close parenthesis. In simple terms, the field looks like a bright spot that is strongest at the fiber center and gently rolls off toward the edge, similar to how a flashlight beam is brightest in the middle and fades outward. Higher order modes have more rings, nodes in the radial direction just like ripples on a pond. The spread in beta values among modes is what creates intermodal dispersion. Different modes arrive at the fiber output at slightly different times because they travel at different speeds. A graded index GI fiber does not have an abrupt change in refractive index. Instead, the index in the core slowly decreases from the center to the cladding, usually following a parabolic profile. N of R equals N sub 1 times open bracket 1 minus 2 delta times open parenthesis R over a close parenthesis to the power alpha close bracket for R between 0 and A, where N sub 1 equals refractive index at the fiber axis, R equals 0. Delta equals open parenthesis N sub 1 minus N sub 2 close parenthesis divided by N sub 1 is the relative index difference. A equals core radius. Alpha is approximately 2 for a perfect parabola, most commercial multimode fibers. If you plot N of R, you get a smooth hill shape. The index is highest at the center and slopes down toward the edge, much like the speed limit in a city that gradually reduces as you approach the outskirts. Light rays entering the fiber follow curved trajectories, continuously bending toward the higher index center, similar to how a marble rolls down a gently sloping bowl and keeps being pulled toward the bottom. Because the speed of light in the core depends on the local index, rays that travel near the center high index move slower, while those farther out low index move faster. This clever trick makes different rays arrive at the far end at nearly the same time, dramatically reducing intermodal dispersion. Explanation: to see how a graded index, GI, profile reduces intermodal dispersion, picture a set of light rays launched into the fiber at various angles. In a step index fiber, each ray travels in a straight line inside the core and reflects off the wall. The longest path, high-angle ray, is much longer than the shortest path, near-axis ray, causing a large spread in arrival times. In a GI fiber, the index varies as N of R equals N sub 1 open bracket 1 minus 2 delta left parenthesis R slash a right parenthesis squared close bracket, parabolic alpha equals 2. The ray equation derived from Snell's law leads to a harmonic oscillator-like motion. D squared R over dz squared plus open bracket left parenthesis 2 pi over lambda right parenthesis squared N sub 1 squared times 2 delta times R divided by a squared close bracket equals 0. Which has the solution? R of z equals R sub 0 cosine of open bracket 2 pi over lambda times N sub 1 times square root of 2 delta times z divided by a close bracket. The ray follows a sinusoidal path, continuously curving toward the axis. The period of this sinusoid, the distance after which the ray returns to the same radial position, is z sub p equals pi times a divided by n sub 1 times square root of 2 delta. Because all rays, regardless of launch angle, complete an integer number of half periods over the same fiber length, their average axial speed becomes the same. Mathematically, the group delay for any mode is tau equals n sub 1 times L divided by C times open bracket 1 plus delta divided by 2 close bracket, which is independent of the ray angle. The result is a huge reduction, often greater than 10 times, in intermodal dispersion compared with a step index fiber. A friendly analogy: imagine runners on a circular track. In a step index fiber, each runner runs straight across the field. The ones on the outer lane have to run farther. In a GI fiber, the track is banked so that even though some runners start on the outer lane, the banking guides them inward, and everyone covers roughly the same distance in the same time. The bandwidth of a multimode graded index fiber is limited mainly by residual intermodal dispersion. A widely used empirical formula for the pulse broadening delta T due to modal dispersion in a parabolic graded index fiber is delta T approximately equals delta divided by C times L over square root of 2 times open parenthesis lambda over a close parenthesis squared, where delta equals relative index difference, C equals speed of light in vacuum, L equals fiber length, lambda equals operating wavelength, A equals core radius. The 3 dB bandwidth, B, is roughly the inverse of the pulse spread. B approximately equals 0.44 divided by delta T. Core radius A equals 25 micrometers. Relative index difference delta equals 0.01, typical for OM3 fiber. Wavelength lambda equals 850 nanometers, which is 0.85 micrometers. Length L equals 300 meters. First compute delta T. Delta T approximately equals 0.01 divided by 3 times 10 to the 8 times 300 divided by square root of 2 times open parenthesis 0.85 divided by 25 close parenthesis squared seconds equals 0.01 divided by 3 times 10 to the 8 times 300 divided by 1.414 times open parenthesis 0.034 close parenthesis squared seconds equals 0.01 divided by 3 times 10 to the 8 times 212.1 times 0.00116 seconds approximately equals 0.01 times 0.246 divided by 3 times 10 to the 8 seconds, which is about 8.2 times 10 to the minus 12 seconds, or 8.2 picoseconds. Now the bandwidth, B approximately equals 0.44 divided by 8.2 times 10 to the minus 12, which is about 5.4 times 10 to the 10 Hz, or 54 gigahertz. For a 300-meter link, this corresponds to a bandwidth distance product of roughly 54 GHz times 0.3 km equals 16 GHz kilometer, which matches the typical specification of OM3 fiber, approximately 2000 MHz kilometer at 850 nanometers when accounting for additional factors. This shows how the graded index design pushes the bandwidth far higher than a step index fiber of the same dimensions. The formula above assumes only modal dispersion. In practice, material dispersion and waveguide dispersion add small extra terms, especially at longer wavelengths, for example 1310 nanometers or 1550 nanometers. Comparison table, step index versus graded index. Properties, step index multimode, graded index multimode. Core index profile, constant n sub 1. Abrupt drop to n sub 2 at r equals a parabolic or near parabolic decrease from n sub 1 at center to n sub 2 at r equals a. Attenuation typical, 2 to 3 decibels per kilometer at 850 nanometers for older fibers. Modern step index rarely used for long runs. 2 to 3 decibels per kilometer at 850 nanometers, but often lower, approximately 1.5 decibels per kilometer at 1310 nanometers, because the index grading reduces scattering. Intermodal dispersion. Large, tens of picoseconds per kilometer for 50 micrometer core, limits bandwidth to a few hundred megahertz kilometer. Very small, approximately 1 picosecond per kilometer for 50 micrometer core with alpha approximately 2, bandwidth distance product greater than 10 gigahertz kilometer. Bandwidth distance product, about 0.2 to 0.5 gigahertz kilometer for old step index, about 1 gigahertz kilometer for small core designs. 10 to 20 gigahertz kilometer for OM1 or OM2, up to 500 gigahertz kilometer for laser-optimized graded index fibers such as OM3 or OM4. Typical use cases: short-haul legacy LANs, sensor interconnects, cheap plastic fibers for low-speed links. Modern high-speed LANs, 100 megabits per second, 1 gigabit per second, 10 gigabits per second, data center interconnects, video distribution. Dispersion types, dominated by modal dispersion. Material dispersion modest at 850 nanometers. Modal dispersion largely cancelled. Material dispersion becomes the limiting factor at longer wavelengths, 1310 nanometers, 1550 nanometers. Manufacturing complexity. Simple single material for core, one cladding material. Requires precise control of dopant concentration radially, for example germanium or phosphorus, thus higher cost. Key takeaways for exam students. 1. Attenuation is mainly a material property. Both fiber types use similar glass, so their decibel per kilometer values are close. The graded index does not magically reduce loss, but better manufacturing often yields slightly lower attenuation. 2. Bandwidth distance product is the decisive metric. Step index fibers suffer from large intermodal dispersion, giving a low product, approximately 1 GHz kilometer. Graded index fibers equalize ray path lengths, raising the product by an order of magnitude or more. 3. Dispersion. In step index, dispersion equals modal plus material. In graded index, modal part is almost null. The remaining dispersion is material and a residual wave guide term. Therefore, at 850 nanometers, graded index fibers can carry 10 gigabits per second over 300 meters, while step index cannot. 4. Practical implication. When a problem asks which fiber is better for high-speed LANs over 500 meters, the answer is graded index, ohm3 or ohm4, because of its superior bandwidth distance product and low modal dispersion. 5. Remember the parabolic index law, n of r equals n sub 1 times open bracket 1 minus 2 delta times open bracket r over close bracket squared close bracket. The exponent alpha equals 2 yields the optimal cancellation of modal dispersion. 6. Design tip. To make a step index fiber act more like a single mode fiber, shrink the core radius so that V is less than 2.405. This is how modern single mode telecom fibers are built.